All right, working. Good morning. So these are the topics that we are going to discuss today. Okay? So this is 23rd lecture in this course, and today we are going to see a generic way, or rather the standard way, of converting a state space model to a transfer function model. Okay. So on the previous class we saw how we can convert a transfer function model to a state space model, because by definition we know that if we have a transfer function model, then we also have a state space model, obviously. Okay, because when we construct a transfer function model, we are assuming quite a few conditions, but in case of a state space model, we are not assuming any conditions. So even if I have conditions, then it only simplifies the state space model, nothing else. Okay, and I have already told you that in this course we are not going to consider nonlinear systems or time variant systems, but those can be also easily modeled using the state space technique. Other than that, we are going to consider non-zero initial conditions, systems that have non-zero initial conditions, and systems that have multiple inputs and multiple outputs. All right. And as usual, during the class, if you have any query, just feel free to ask. I'll be answering your queries. All right. So let's get started. We recall our state space model look like this. For any system, for any linear time invariant system, the state space model look like this. So I would say for any continuous time LTI system, the state space model, rather let me just write it down. So for any continuous time linear time invariant system, the state space model actually has two equations, right? One is the state equation, the other is the output equation. The state equation is a first order differential equation. Of course, it's an n number of first order differential equations, first order linear ordinary differential equations, and this is represented with this. So this is the derivative of the state vector, and that would be equal to matrix A, which is the system matrix, multiplied with the state vector plus B times U, and of course U is a vector quantity here, and output, which I am assuming to be a vector quantity, will be C x plus du. Here C is known as the output matrix and D is known as the measurement matrix, and whenever I am putting underline here, it would indicate that it's actually a matrix or a vector. Okay, and now whenever I am writing uppercase letters, it means it's a here uppercase letter with an underline means it's a matrix or a vector quantity, but it's a constant term. Okay, so A, B, C, D, these are constants for any single plant or single system here. Okay, they do not vary with time. That's the important part to understand here. All right, so with that said, we have these are the equations, right? Now if I give you, I told you earlier that the way we were doing the state space modeling is known as the phase variable canonical form, and even in that we have multiple notions of how we can use state space the phase variable canonical form, right? Some people uses phase variable canonical form in the reverse way. Okay, so they consider x3, for example, if you have a third order system, they would consider x3 to be equal to y, okay, x2 to be equal to y dot, x1 to be y double dot. Okay, and we considered x1 to be y, x2 to be y dot, x3 to be y double dot, things like that. Okay, so you can understand not only that, and we are going to prove that later on, that a single system, a unique system that has just a single transfer function can have, rather does have, infinitely many equivalent state space representation. So a single unique system has equivalently many infinitely many equivalent state space representations. So it is not always easy to figure out the transfer function from a state space model, right? But if I give you the canonical form, a phase variable canonical form, you can, from that, those values in the phase variable canonical form, you can figure out the uh, transfer function by just looking at it, by just inspection, right? Because if you solve a problem, basically if I give you a transfer function and from that if you construct the state space model from that, you would see that the coefficients from the transfer function actually are reaching certain places, right? And from that you would have an idea on what to do with those, right? You would have an idea of how to construct the transfer function back from the state space. But if I give you a generic state space model where it might not conform to any canonical form, in that case, and that might still be representing the same system in that case. So in that case, if you want to figure out the transfer function, you cannot just follow that method, right? You cannot just follow that method. Now here, I want you to notice something very important here, is that this x here, this x quantity, this entire thing, this x is not a scalar quantity, okay? This x is a vector quantity. And not just that, this x is indeed a function of time. So this is a vector which is a function of time, okay? So it is essentially, if it's an nth order system, it is essentially carrying all the states, that is x1t, x2t, and so on up to xnt. So it is carrying all the states, and states are individually kind of descriptors, variables that determine the output of the system, for example. Okay, so essentially it's a vector that has a dimension of n by 1. So essentially it's an n by 1 vector. Let me write it here. Okay, but here every single individual element here are functions of time, right? All of these are functions of time, right? So really, ideally, I should not have written it this way. Ideally, I should have written this this way. Let me just say, I should have technically written this way to make sure that you understand that this is a function of time. But then again, we can get away with not writing those t, because it is inherently assumed that all these variable quantities, see, a, b, c, d are constants, but the variable quantities are x, u, and y. They are functions of time. So the input is a function of time. So these are assumed inherently. The output is a function of time. Okay. Of course, the state vector is a function of time. So the derivative of the state vector is also going to be a function of time. Okay. And so like that. And of course here. So that should be, that is how we should really write it. Okay. But then again, we can skip writing t, because it is inherent. It is assumed literally that these are functions of time. Okay. So this is understandable, I think. All right. So with that said, on this, now we want to construct. So this is, see, in this is a state space model. Try to understand. So this entire thing is a state space model, right? So this is the state equation, and this is the output equation, right? So this one is the state equation, and this one is the output equation. State equation, output equation. Now this is representing a linear time invariant system. Okay, so that is the only, these are the only conditions we are imposing, right? We are not considering the system to be a seesaw system. Neither we are considering the system to have zero initial conditions. So we are not imposing those conditions, right? We are not considering the system having zero initial conditions. We are not considering that it's a seesaw system, right? So those conditions have been removed, really. Okay, so we have a linear time invariant system. So this is the condition that is imposed, right? So I can say this is, so I have written it, right? So this for a continuous time linear time invariant system. So this is the state space model. Now if I want to construct the transfer function, figure out the transfer function from the state space model, I have to impose one condition, right? The condition of zero initial conditions, right? The condition that the system would have zero initial conditions. Otherwise, see, this model can actually, and we will see later on, that this model, okay, this state space representation can handle non-zero initial conditions pretty easily. Okay, But if I want to construct the transfer function model out of this, we have to understand that we have to assume, in addition to whatever we have to assume zero initial condition on top of the state space model. Then only we can construct the transfer function model, right? Out of that. You understand this, right? Because if I want to go back to transfer functions, then we have to impose the condition that came alongside transfer functions, right? So just keep that in mind. Okay, so with that said, let's apply Laplace transform on these equations. So applying Laplace transform assuming zero initial conditions again. Again, just so that you take it, you understand this clearly, is that the state space model does not impose any condition like this, but only because we are trying to figure out the transfer function model out of this, we have to impose this condition in addition to whatever we have, because the transfer function model requires that we have zero initial conditions, right? Now out of this equation, let's consider the first equation. This is the equation, right? This is the equation. So xt is what should I say, xt here is a function of time, right? Now if I take a Laplace transform on this, okay, try to understand that xt is a function of time. Let me just copy and paste this. Xt is a function of time. Okay, now if I take a Laplace transform on this essentially becomes a Laplace transform on the whole thing, right? Laplace transform on the whole thing. So I would say that I would rather call that, so if I take Laplace transform on this, then I would write something like this. So Laplace transform on this entire vector. But how can I write a Laplace transform on an entire vector? Just take the Laplace transform on each individual elements of the vector. So I'm taking a Laplace transform on individual elements of the vector. So essentially it is taking Laplace transform on x1, x2, x3, x4 up to xn. So all the individual elements are taken that way, right? So that way it is essentially going to be really something like, so again we have to understand that we know about x1, x2, x3 individually, right? So this is going to be x1s, this is going to be x2s. Now here is a change in notation, because now we are writing uppercase letters, but since we are using Laplace transform, we have to understand the uppercase letter now indicates, since we are writing s in the bracket, it indicates that it's a function of s really, right? So now a, b, c, d are again constants, but we are writing s to explicitly mention that these x1, x2, these things are in the frequency domain, right? And this quantity, which is the Laplace transform of this, Laplace transform of xt, is now going to be xs, now with an underline. This would indicate that this is the Laplace transform of the state vector. So this is the Laplace transform of the state vector. Okay, so I would say Laplace transform of the state vector. Of the state vector. All right, that's the Laplace transform of the state vector. So if that is so, then question is, what is the Laplace transform of the derivative of the state vector? So what is the Laplace transform of this, the derivative of the state vector, right? So if you think about it, what is the derivative of the state vector? The derivative of the state vector is essentially this entire thing really, okay, this thing really, but all the individual elements have their derivatives instead of themselves, instead of being by themselves, right? All right, so this will have a derivative term here. So essentially, how do you take that? So what is this x dot t, the derivative of the state vector? So that is essentially something like this. All the individual elements have derivatives like that. So we are talking about this term here, right? The derivative here, right? So taking a Laplace transform on this again means taking a Laplace transform on this entire thing, and that would result into a Laplace transform of the individual elements. But if the Laplace transform of x1t is x1s, then what is the Laplace transform of x1 dot What is the Laplace transform of x1 dot? That would be s x1 s. Notice the use of uppercase letters. So this would essentially indicate that I have switched the variables to the frequency domain. So now this is the Laplace transform of the derivative of the state vector. So this is the Laplace transform of the derivative of the state vector. But notice very carefully that I can that from this I can okay. Now from this, notice that I can bring the s outside, right? So that is something I can factor out, right? And if I can factor this out, then technically this just becomes this, right? Which is just equal to s xs, because this term here is nothing but this term, and which is indeed xs, which is the Laplace transform of the state vector itself. So you can understand that if you think about this next line here that I have written here, the derivative of the state derivative of the Laplace transform of the derivative of the state vector is essentially s times the Laplace transform of the state vector. So this rule that when I apply derivative to a function, then its Laplace transform becomes s times that is still applicable here, right? Only matter is that we are assuming zero initial conditions here. Otherwise it would really be s x1 s minus small x1 0, really. Okay, so we are assuming zero initial conditions, so keep that in mind. Here we are assuming zero initial conditions. Zero initial conditions. Otherwise, really speaking, this is going to be sx1, okay, and minus x0 minus, so that's a 0, x1 0 minus x2 0 minus, and such and such, right? So we're assuming zero initial conditions, so all these are zeros, so essentially they cancel out automatically, they do not appear anywhere, right? So I think this is understandable, right? And obviously the Laplace transform of ut is us, Laplace transform of ut is us, Laplace transform of yt is ys, the same way, right? It will be a vector and we are taking the derivative, the Laplace transform of each individual element, right? So now if I take this equation, okay, so this is the state equation, right? Let's bring this, and if I apply Laplace transform on this, so this is the state equation, right? And if I apply Laplace transform on this, okay, then assuming zero initial conditions, oh, what have I written? Okay, that copy paste went wrong, really wrong. Thank you very much, someone is really following this, right? I actually somehow tried to copy this, but it did not get copied properly. Absolutely, you are right. So thank you very much for correcting this. Yes, I actually tried to copy this, but somehow the previous one got copied. Okay, I think there is no issue understanding this, right? All right, so with that said, now apply Laplace transform assuming zero. So this is the state equation, right? Now applying Laplace transform, let me just write LT, I think you would understand, right? Assuming zero initial conditions. Now I am writing assuming zero initial conditions, but instead I am going to just say assuming zero initial conditions mean that this vector, this thing, when t is equal to 0 is a vector of zeros, like that. Okay, so that is the zero initial condition here. Okay, essentially that is what it means. Okay, it means that this vector when t is equal to 0, that x1 0 is 0, x2 0 is 0, x3 0 is 0, and such. All right. All right, so with that said, I'm going to consider that a vector of zeros, so I would write this I think you understand what I'm writing, right? So this is the vector of zeros. Assuming, so this is 0 initial conditions, right? Right. So let's apply Laplace transform here. So here I know if I apply Laplace transform on this, this would become s xs minus x0, okay, equal to a xs plus b us. Okay, so everything has got Laplace transformed, but this is going to be considered to be 0, right? Because we are assuming 0 initial conditions. So this is a 0 vector. Okay, so that, notice the underline here. Okay, that's a vector, a 0 vector. So all the elements are 0 in that state vector, right? So with that said, okay, with that said, now we can write the equation simply becomes x sxs minus, sorry, what am I writing? All right, it's fine. I think again our objective here is to figure out a general way of calculating the transfer function from the state space model. So now I can bring this term to the left and take this s. So let me just do that. Okay, let me just okay, fine. All right, so now let me take this excess common out of this, but notice very carefully that this is a matrix product. This is a matrix product. Okay, so since this is a matrix product, I have to keep the order right. So now of course that would result into an a here, and now I have s here. Is that so? So are we so s is a scalar quantity. Are we subtracting a scalar quantity from a vector, or rather a vector quantity from a scalar? The matrix from a scalar. A is a matrix here. S is a scalar quantity. Are we doing that really? To understand what is happening here is that, say I want, so this is there. Okay, these are all matrices. A and B are matrices, right? If I want to take A common out of this, factor out of this, I have to write AI minus B. So I would be the identity matrix, right? That way, if you just do the multiplication again, it becomes A times I, but again A times I is just A because A is the identity matrix, and then that is what we have, right? In the same way, this S can be assumed to be SI, right? This S can be assumed to be SI. So I would have SI minus A. Yes, we can multiply identity matrix, and that is what we have done. Identity is equivalent to writing 1, okay, in the matrix domain. Okay, and here is called the multiplicative identity here, and this is right, just like that. All right, I don't think there is any issue there. All right, again, whenever we are doing matrix multiplication or whatever, it is very important to remember where these things were, right? So say for example, if I write A B in the matrix form, again equal to C, then B is equal to A inverse C. So the order is pretty important here, right? So technically what we are doing, in order to achieve this from this, we are actually, what we are doing, we are multiplying both sides with A inverse. So I would have A inverse AB equal to A inverse C, and that thing actually results into an I. So this becomes I B, and that actually gives you A inverse C. Okay, and IB is obviously B, because multiplying anything with an identity matrix, that gives you that. But say if you did that the other way around, if you just did the multiplication other way around, so if you say A B A inverse, okay, that would just be C A inverse, and that would make no other simplification possible. Okay, there won't be any other simplification here, right? Because these A and A inverse, they won't get multiplied to identity, right? They have to be side by side. So the order in which you are doing the you are doing the multiplication is very important, because because matrix multiplication is not commutative in nature. Usually, I mean by default, this is the usual case. AB is not equal to BA. So matrix multiplication is not commutative. So that's not true. So and because of that, the order in which you are multiplying these things is important. Okay, I think that's understandable, right? So because of that, you have to maintain the order. So if I want to get rid of this term here, okay, if I want to get rid of this term here, I have to bring this term here. So that will get an inverse essentially. So I'm essentially multiplying both sides with the inverse of this quantity, right? That way I'll get rid of this from this side, but I have to then multiply with the inverse of this quantity to the right hand side. So what I am talking about is this. I would have xs here, and on the right hand side I would have si minus a whole inverse. See, that's the whole inverse, okay, times b times u, which is a function of s, right? So that's the state vector representation of the Laplace transform of the state vector. Okay, representation of the Laplace transform of the state vector. So let's skip that. Let's skip this. Okay. Now with this, now let's apply Laplace transform to the. So this is the state equation, right? Let's take the output equation. Okay. Let's take the output equation. Okay, so this is the output equation. All right. And here let's apply the Laplace transform again. And here we don't have to assume zero initial conditions. Apply just Laplace transform, because we have already done assuming applying Laplace transform. What do I get? We get ys, because we are assuming the Laplace transform of yt is ys. Okay, and again that's a vector quantity. Okay, that's a vector quantity. And here with the Laplace transform of this is essentially c is a constant here, so this is going to be this. Again, d is a constant here, so this is going to be this. All right, but then try to see that we already have an expression for xs. So let's put this expression of xs here. So whatever we have in the place of xs, let's put that here. Okay, so if we do that, which now yields ys equal to c. Now that's a vector matrix here, and instead of xs I would write this quantity. Again, since I can happily copy paste, I would happily copy paste. And then we have, just as usual, plus d us. Okay, we just copied and copy pasted these terms. Right? Now notice very carefully here, there is one important point to notice here, is that we are by default assuming a MIMO system, multiple input multiple output system. That is why the output is a vector quantity, the input is also a vector quantity. Okay, the input is a vector quantity because we are assuming multiple inputs, and the output is also a vector quantity because we are assuming multiple outputs. But transfer function really works when we have single input single output, right? Otherwise we would have something called the transfer function matrix, okay, which I don't want to go to right now. So now if we assume the CISO condition, okay, right? So now assuming the system to be CISO, I don't understand. Then if I assume that the system to be CISO, single input single output, then essentially u is a scalar quantity. It's just ut, right? So that's the input technically, and that's just a scalar quantity. So I can write this equation, and so if I have single input, then I can write this equation, and what I can do, I can get rid of these underlines here, indicating that u was a scalar quantity because I have single input. Just like that, I have a single output. So if I have a single output, then this y, which is representing the output, is also a scalar quantity. So I can get rid of the underline. it is very important to understand that I can get rid of these underlines here. Okay. Okay, so the underlines here are representing vectors or matrices, right? So now with this equation, we can write down ys to be equal to, now look at this equation. So here I can see us and us, so I can factor out us from this. So to do that, I would copy again. I would copy this. Okay, so this is the term we are factoring out. Okay, and let's say, so that's us, right? Sorry, it's a scalar quantity now, right? So now we can bring this us to the left hand side and write ys by us to be equal to c si minus a inverse b plus d. Okay, there is one more thing. There is just one more thing. When I consider the input to be CISO, the system to be CISO, when I consider the system to be CISO, there is just one more thing. Okay, this is a scalar quantity. See, look very carefully. All the dimensions must match. This is a scalar quantity, but the output is also a scalar quantity. So the output must be a scalar quantity. So this d has to be also a scalar quantity. Okay, just keep that in mind. Okay, and someone has asked, how can a scalar quantity be equal to a matrix? I am going to answer this right now. Okay, now let's talk about the dimensions of the matrix. Okay, so you have previously done what should I say? Previously done state space modeling, right? So for example, if I give you, say for example, say if I give you a system, now assume this, if I give you a system that has a one, say for example, that has one input, so this is a system, right? That has one input, right? So I would say one input, and that has one output. Okay, and this is a, say this is a third order system. So you have done modeling third order systems, right? So this is a, say that this is a third order system, right? So say like that. So you have seen, if it's a third order system, you have seen the dimensions, right? You have seen the dimensions. Of course, the matrix X would have a dimension of, so matrix X, okay, so rather vector X, the state vector would have a dimension of n by 1. So it's a n by 1 matrix. So it looks like this. So here it will, so for example, if it's a third order system, it's going to be 3 by 1, right? So it is going to be x1, x2, and so on up to xn, like that. Okay, so again the same order would be for the derivative here, right? Okay, since we have a single input system, U is essentially a 1 cross 1 matrix. Okay, output is also a 1 cross 1 because this is a single, representing a single input, this is representing a single output here. Okay, all right. And matrix A, you saw that matrix A was a n by n matrix, right? So that was an n by n matrix. Okay, so that was an n by n, some elements were there. Okay, I'm not going to represent it canonically, but keep in mind A was an n by n matrix. So for a third order system, it would be a 3 by 3 matrix, right? It is, A is always going to be a square matrix, right? And then you also saw that B, the input matrix, was a n times 1 matrix, right? N by 1 matrix. Okay, so B had elements like this, for example, what should I say, B1, B2, and so on up to Bn, whatever. All right, something like that. So that's going to be n by 1 matrix. And C, then again you saw the C is a 1 by n matrix. So if it's a third order system, then it's going to be 1 by 3. Of course, this depends on the fact that we are assuming one input and one output. All right, and we are going to modify this for multiple input, multiple output shortly. Okay, today. And then we saw that this was a row matrix or row vector, so that is 1 by n, and you would have elements like c1, c2, and so on up to cn. Okay, and just like that. And d would be a scalar quantity, which is again going to be 1 by 1. Okay, so now look at this equation and see that the left hand side is a scalar quantity, because ys is a scalar quantity, us is a scalar quantity. But now think about the dimensions here. Okay, so n here, c, what is the dimension of c? That's 1 by n. Okay, what is the dimension of si minus a? A has a dimension of n by n time, so it's an n cross n matrix. So I is also the identity matrix of order n, so that's also n cross n. So n cross n matrix minus n cross n matrix, so that's n cross n. Okay, b is a n cross 1 matrix and d is a 1 cross 1 matrix, right? Now think about the matrix multiplication rule. So you are multiplying two matrices, say a and b. Okay, they can only be multiplied if this matches. So for example, if a is a m cross n matrix and b is a n cross p matrix, for example. Okay, so if the inner dimension of the first matrix matches with the inner dimension of the second matrix, then only they can be multiplied. And whatever you get as the result has a dimension of the outer dimension of m and the outer dimension of p, outer dimension of a and outer dimension of b. So that's how matrix multiplication works, right? So the number of columns in matrix A should be equal to the number of rows in matrix B. Then only AB, this multiplication can happen. And then the resulting matrix would have the number of rows equal to the number of rows of the A matrix and the number of columns equal to the number of columns of the B matrix. Right? That is how the multiplication is possible. Okay? And right? So now think about it. Think about this one. So question is this multiplication possible? Is this multiplication possible? So let's take this from the left hand side. Is this multiplication possible? Yes, this multiplication is possible because the inner dimensions are matching, right? But what is the result if I multiply these two? So if I multiply c with the inverse of si minus a, okay, so if I multiply these two, the result would be simply a 1 cross n matrix, because the result would be the outer dimensions, right? So here in the outer dimension we have 1 and here the outer dimension is n. So again, this multiplication is possible. I can multiply this c with this because the inner dimensions are matching here. Okay, and here look at the outer dimensions. So that will be the dimension of the resultant matrix. And now whatever I get out of this will get multiplied with b. Now here look very carefully. There also the inner dimensions are matching, right? So whatever I get out of this gets multiplied with b. Now there, notice that the inner dimensions are again matching. So this n and this n are matching, right? And what will be the result of this product here? What is going to be the dimension of the product here? Okay, what is going to be the dimension of the product? Of course, that would be the outer dimensions here. What is the outer dimension here? 1 here, 1 here. So if I multiply these things, this entire thing, after doing the entire multiplication, this just becomes a scalar quantity. So this just becomes a scalar quantity. So it's a 1 by 1 matrix, which is a scalar quantity, right? So this just becomes a scalar quantity. And then we are adding it with d, and d is already a scalar quantity. So we're adding a scalar quantity with a scalar quantity, and of course getting a scalar quantity. Right? Right? And what is this scalar quantity known as? This scalar quantity is the ratio of the Laplace transform of the output of the system to that of the input of the system when I assumed 0 initial conditions, and I also assumed that the system has 1 input and 1 output. So this is the ratio of the Laplace transform of the output to that of the input for a continuous time seesaw LTI system under 0 initial conditions. So this is nothing but the transfer function. So the transfer function of a system that is represented by using state space is this. Now I told you earlier that a single system that has a unique transfer function has infinitely many state space representations, right? But even if I give you 1,000 different state space representations of the same system, right? If you calculate this would be unique. Okay, So even if I give you 1,000 different state space representations of the same transfer function, and I can give you those, okay, if you calculate this, you would surprisingly see that you are ending up with the same transfer function. Okay, so I told you a unique transfer function has infinitely many state space representations, and from those state space representation, if you go back to the transfer function, you will always end up with the same transfer function. Okay, so this is designed in such a way. Okay, this is so wonderful, and we are going to prove this mathematically. Instead of solving thousands of problems, we are going to prove this mathematically that this is true, really. Okay, so keep that in mind. So this is the transfer function of a system. So I can now happily copy this and paste this and say the transfer function is just this. Now I'm saying equal to, and I'm very careful about when I write equal to and defined as. So transfer function is not defined this way, but it is just equal to in this particular case. Okay, this is really never the definition of transfer function, in no way. But if I have a state space model, then this is the equivalence relationship between the corresponding transfer function model, if I neglect the initial conditions and if I assume the system to be FISO. If you have any query, just feel free to ask. And again, in the last class, you saw how you can use Python to actually convert a state space model to a transfer function model. This is exactly what Python was doing under the hood. You gave it transfer functions, it did calculate this, and you gave it A, B, C, D matrices, the state space model essentially, and it calculated this thing to give you the transfer function back. All right. So I think time for a problem here. And don't worry, we are going to see quite a few things about this. See, I want you to learn the state space modeling very or rather properly. Okay. See, if you don't have any difficulty understanding this, just ask. So I shall continue then. If you have any query, ask. Otherwise, I shall continue. All right. I think there is no query. All right. So again, I told you, if I give you a transfer function, or if it is in the, if the state space model is in the canonical form, then you can very easily calculate the transfer function, right? Just by looking at it. Right? So that's not an issue. But if I give you a transfer function that looks something random, for example, let's say, so say for example, time for an example. Say, let's say a good example. Let's take a good example. Okay, example. So I am constructing the example right in front of you. Okay, say I have a transfer function that looks like this. Okay, say 2s plus 3 divided by s square 7s. And I am right now not going to tell you how to construct the state space model of this, really. I'm going to talk about that later. Okay, but I am going to say this is what the state space model really looks like. Okay, from this. Again, we are going to talk about this at a later class, don't worry. Okay, so say we have this this, and this is the state space model, and I'm not even going to tell you what I'm assuming to be x1, what I'm assuming to be x2. I'm not going to tell you anything of that sort. I'm just going to tell you the state space model. Okay, so this is the transfer function, and the corresponding state space model, okay, would would look like this: x1 dot equal to, you know, that's going to be ax. And let me tell you what ax is. Okay, what a matrix is. A is 0, 1, minus 9, minus 7. Notice the terms, where the terms are going. Okay, and that will be multiplied with x, and that would have a plus. ZW. Okay, so U is my input. Again, U does not stand for unit step, and the output equation would be, that's going to be again, once you are familiar with how this thing works, and then 0U, once you are familiar with this thing, how these things work, really just by looking at the transfer function model, you'll be actually able to construct the phase variable canonical form state space model. So this is state space model in the phase variable canonical form, not exactly, but very close to that. Again, you are going to know that distinction later on. So now say, again, I'm going to teach you how to construct the state space models for things like this, because if you recall, whatever we studied in the last class, we never considered, in those examples, we never considered anything in the numerator. We only considered something in the denominator, right? My numerator was just 1 for those examples, right? Here we have something else, and you can notice what happened. Those elements somehow appeared here. Okay, so you can pretty much notice what really went where, right? This 7 went there as a -7, this 9 went there as a -9, this 2 went there as a 2, this 3 went there as a 3. Okay, and something like that. Okay, you can notice there. Of course, this is your matrix A, this is your matrix B, this is your matrix C, and this is your matrix D. Okay, this 0 is matrix D. Okay, so I can just keep writing this. You have to assume that if D is not there, it means D is equal to 0, right? So that's the state space model. Imagine you don't know this. So I just started with this, but imagine you don't know this yet. Okay, imagine you don't know this yet. Okay, so imagine I gave you the state space model here, okay, and asked you to calculate the transfer function. Now if you are, so if this is given in this way, which is called the phase variable canonical form, then in this canonical form you can just look at these values. Okay, say okay, I have -9, so it will be 9 here, -7, it will be 7 here. So you can just look at the form. Okay, 3, then it's a 3, it's a 2, it's a 2, it's a 2, right? You'll automatically be able to understand what's happening here once you get accustomed with these things. Okay, now here notice very carefully that imagine we don't know this. Okay, and I told you that this model is not the only model for this system. This system can have infinitely many different state space representations. Okay, this system can have infinitely many different state space representation, and how to construct those infinitely many state space representations I am going to teach you. Okay, I am going to teach you how to construct those infinitely many state space representations. Okay, not because you can, but because you would need. Okay, we are not going to construct infinitely many state space representation because we can. We're not going to do that, but we are going to construct many state space representations of a same system because we would need many different representations depending on what purpose we want to put it to, right? So sometimes having many choices is not a good thing, but here in this case at least having many choices is a good thing, right? Again, I told you earlier, so if I want to see certain insights about the system, one type of state space model would be nice. If I want to design a controller for the system, one type of state space model would be nice. If I want to design an observer, and what is an observer, I'm going to tell you. Okay, if I want to design an observer, then again another kind of state space model would be nice. Okay, so there are different types of state space models that serve different purposes, but they are equivalent. So if you calculate the transfer function, you will get the same thing out of those. But then again, so just for the moment, let's calculate the transfer function using the definition. Okay, so we know that the definition of the transfer function here. So question would be examples, and in this example the question is going to be same. The question is going to be calculate the transfer function from the following state space model. I don't use the term SS really because that sometimes refers to steady state. Okay, that's a more common use case of writing SS. Okay, so again, since we are talking about state space, we can safely assume that you're not going to get confused, right? All right. So with that said, let's use the definition, very definition of transfer function, right? So we know that the transfer function, okay, again, this is a single input, single output system, because we can see u is a scalar quantity, y is a scalar quantity. That pretty much tells me that it's a single input, single output system. So I have a proper transfer function. Otherwise, I would have something called a transfer function matrix that relates every single input to every single output. Okay. So if I have 3 inputs and 4 outputs, then in the transfer function matrix, we would have 12 elements that relates 3 inputs to each of the outputs. So every output will have a transfer function relationship with every input. That way, I would have 12 transfer functions representing a same system. That is how things become very difficult. All right. So anyway, so the expression is C times Si minus A whole inverse times B plus D. Okay. So that's the transfer function, right? So let's write those down here. Okay. So what is C? C is this matrix, right? Again, the moment you think that it's becoming difficult for you to understand, feel free to ask. I'm always there to help you. All right. So then we have Si. But what is Si? What is Si? So Si essentially is S times the identity matrix of order 2, because A is a matrix of order 2. So I is also going to be a matrix of order 2. So square matrix of dimension 2, right? So it's going to be 1 0 0 1. So that's the identity matrix of dimension 2, right? And minus A. So A is what is this? 0 1 minus 9 minus 7. So 0 1 minus 9 minus 7. Again, we are doing this just to prove a point. The thing is, if I give you the transfer Statespace model in this way, like this is the phase variable canonical form, just by looking at it, you can write down the transfer function. Okay, but there are infinitely many other forms in which you won't be able to write down the transfer function just by looking at it. But again, my point is, why would you even bother calculating the transfer function from a state space model? Because state space model is a far superior structure than transfer functions. This is mostly for the academic interest here, and this is for the fact that we are going to prove a very important point out of this. Okay. Si minus A inverse, and then we have B. Okay, and plus D. So essentially plus D, and D was 0, so I'm not writing that. D is 0 here. Okay, you can see that D is 0. So this, let's just write 0 U. So that's D. D is 0 here. All right. So not writing. So let's just who cares? Really, adding 0 doesn't change anything. Okay. So we have to take care of this internal part here. Okay. So let's just write. So this is 3 2. Okay. So now this is S0 0 S minus this matrix. So this becomes S minus 1 9 S plus 7, the inverse of that. So inverse matrix of this. Okay, and then I have 0 1. Got it? All right. So now we have to take care of the inverse first. All right. So now here is a problem. Let's calculate the inverse of this matrix, but let's see what we get out of this. Okay, if I take the inverse of this matrix, so this is Si minus A inverse. Let's just do this calculation separately. Okay, instead of messing this thing up, let us just do the calculation separately. So this is what this is. This is the Si minus A matrix, right? So this is Si minus A. Okay, so rather say Si minus A inverse. So this is your Si minus A inverse. So this inverse matrix is this. Okay, so how do you calculate the inverse of a matrix? You calculate the inverse of a matrix by calculating the, so if I say, if I want to calculate A inverse, so that would be simply the adjoint of A by determinant A. Adjoint of A by determinant A, also known as adjugate. Okay, I rather would call this adjugate. Okay, I learned this it the hard way. The modern terminology is not adjoint. Adjoint means something else. Okay, in modern mathematical terminology, adjoint means transpose, and this is really called adjugate here. Okay, so this is the adjugate of A divided by the determinant of A. Okay, all right. So really speaking, what is the SI minus A inverse? What is SI minus A in SI minus A whole inverse? SI minus A whole inverse. Let's just clear this up. So what is SI minus A inverse then? SI minus A inverse would be the adjugate of A times 1 by determinant. So I'm going to say 1 by determinant of SI minus A, okay, times adjugate of SI minus A. All right, so that's true. What is transjugate? What? I don't know. All right. So again, adjugate SI minus A divided by determinant SI minus A. So I know that, right? So if I know that already, then I can say, okay, what is this? What is the, okay, let me just bring this to the next page rather. It would be better. So now we are calculating the inverse of, so we are calculating this. So that is what we are calculating, right? So this is your SI minus A inverse, and that would be equal to 1 by determinant this. So S minus 1, 9, S plus 7, and adjugate this. Very funny. All right. All right. So you people know how to calculate this. So notice we here in that so here while we are calculating the determinant here, that just simply becomes S times S plus 7 plus 9. Nice. And here the adjugate for 2 by 2 matrix is very simple. It is just, you just change the exchange the elements in the principal diagonal, and for the other diagonal just put minus signs. So it becomes S plus 7 S. So this becomes 1 and this becomes minus 9. Correct? So now here what we have is 1 by S square plus 7S plus 9, and here we have S plus 7. See this S plus 7, 1 minus 9 S. Now notice that this is a scalar quantity. This entire thing is a scalar quantity because that came from a determinant, right? This is a scalar quantity. But what is this? What is this? So notice very carefully, that is a scalar, especially this one is a scalar quantity. But what is this? Isn't it the same thing as this? Notice something. Okay, once we did that, what is this? This turned out to be whatever I got out of the determinant actually gave me the characteristic polynomial of the transfer function. So this is one of the most important points that you have to notice here. What I got out of the determinant there, okay, so that was the determinant. What I got out of the determinant there is the characteristic equation of the transfer function itself, the characteristic polynomial of the transfer function itself. Okay. So before I proceed, let's see where that came from. Before I proceed, let's see where that came from. Okay, where this term came from. So notice, where did this term come from? This term actually came from the determinant here. This is the determinant from which this term actually came. But what is this determinant? So this is the determinant of Si minus A, right? Determinant of Si minus A. So I am saying here that I'm seeing that the determinant of Si minus A is actually equal to the characteristic polynomial of the transfer function. Okay, all right. So that way, then therefore I can say, if I write the characteristic equation, so what is the characteristic here in this one? The characteristic polynomial is this. So this equation, therefore, here in this particular example, determinant of si minus a, in this particular example, this is equal to s square plus 7s plus 9. So this is the characteristic polynomial. So in this particular example here. So what is the characteristic equation? Then the characteristic equation of the transfer function, what is this? This is s square plus 7s plus 9 equal to 0, can be rewritten as, so this came from the transfer function, right? Can be rewritten as this equation, the determinant of si minus a equal to 0. So this is literally the characteristic equation of the transfer function. So determinant of si minus a is the equal to 0. This equation is the characteristic equation of the transfer function, right? But this is also the characteristic equation of the matrix itself. So you might recall that if, but you might recall, I'm just going to say, you might recall that if lambda are the eigenvalues, lambda is an eigenvalue of a square matrix, someone is saying, why this for particular example? No, I'm just showing you this with this particular example. This is always going to be true. Okay, this equation is always going to be true whatever you try. Okay, that determinant would always, let me going to explain this. Let me explain this. But you might recall that if lambda is an eigenvalue of a square matrix A, then the determinant of lambda I minus A equal to 0. That is something we call the characteristic equation of a matrix, of a square matrix. And by solving this, what we get are the eigenvalues of this, right? So by solving this equation, so this is the characteristic equation of the matrix A. Okay, by solving this, we get the eigenvalues of A, right? So I will get certain values of lambda. Those will be the eigenvalues. Now here, what have we written? We just have replaced essentially lambda with s, right? Lambda with s, right? So I'm going to say this thus rather, okay, this equation not only represents the denominator, rather the characteristic equation of the transfer function, it also represents the characteristic equation of the system matrix itself. And as such, the eigenvalues of the system matrix, so if I solve this equation, what am I going to get? I am going to get the eigenvalues of A, right? Eigenvalues of A. And the eigenvalues are A. So solving this equation is essentially solving this equation. And what is this equation? This equation essentially is solving for the pole locations of the system, right? So if I solve this equation, I am calculating the eigenvalues of A, but in turn, by solving this equation, I am solving the denominator's polynomial of the transfer function. And by doing that, I am actually calculating the poles of the transfer function. So thus, the poles of the transfer function are basically the eigenvalues of A. So if you have matrix A, system matrix, the eigenvalues of A determines the poles. Now here, try to see that I just did this with an example. I showed this with an example, but this is always going to be true because that is what it is, right? So this is the denominator, and in the denominator, you are going to see the determinant of this, and that determinant of Si minus A is going to give you the denominator's polynomial. So if you equate the denominator's polynomial, to 0, then what you are essentially equating to 0 is the denominator's polynomial of the transfer function itself. So by doing so, you are calculating the eigenvalues of A, but the eigenvalues of A would be also the solutions of this polynomial, and the solutions of this polynomial are essentially the poles of the system, and as such, the eigenvalues of the system matrix A are nothing but the poles of the system. And you know that the poles of the systems are very crucial. They determine the stability of the system, right? The stability of the system, the damping, the undamped natural frequency, all those terms are determined by the poles of the system. So matrix A, that is why matrix A is known as a system matrix. It is pretty much representing the inherent behavior of the system by having the poles built into it, right? So matrix A represent the system. That is why matrix A is called the system matrix. Okay, that is why matrix A is called the system matrix, because it is carrying the entire feature of the system, rather the poles of the system is technically, right? So eigenvalues of A are also the pole locations, right? Got it? So with that said, let's go back. So we had this 3, 2. So if I give you a state space model, in order to calculate the pole locations, you don't have to go far. Just take matrix A, and if you have a modern calculator or any computer, whatever, you can always calculate the eigenvalues of a matrix, right? Of a square matrix. Right? Anyway, we calculated the inverse Laplace transform. Inverse of the matrix with this. So this multiplied with so technically I have a scalar quantity multiplied, so I have to bring this outside, right? 1 by s square plus 7s plus, and here we have this matrix. If this happens, copy doesn't work. Okay, and I have to bring this hold on a second, I have to bring this here. So I would have 1 by s square plus 7s plus 9. But notice that again, this term actually came from the determinant of Si minus A, right? Again, instead of writing that in the middle, I'm writing that outside. That is how we should write it. All right. So let's do the multiplication here. So I have 1 by s square plus 7s plus 9. I have 3 times 2 here. Let's do this multiplication first because that is easier, because again this will result into a column matrix, and obviously you can, if you just multiply this, the result is very simple. Here s plus 7 times 0 plus 1 times 1, so that's just 1, and minus 9 times 0 and s times 1, so that's it, right? So this is equal to this, and of course this results into a scalar quantity once again, because it's a 1 by 2 and it's a 2 by 1, so of course it becomes 3 plus 2s. So if I just write it, it becomes 2s plus 3 divided by that. So that's the transfer function again, if you just see. Okay, that's the transfer function. So along the way we learned a few things about this. Okay, so that's the important point, most important point that you should take away from this is this statement here. The poles of the transfer functions are so by saying basically I mean exactly equal to. The eigenvalues of A. Right. And I told you that a same system, a unique system can have infinitely many state space representations, right? And on those infinitely many state space representations, matrix A would look different, but still the eigenvalues would be the same, because if I represent it in a different way, the poles cannot change, right? If I represent it in a different way, the poles will be the poles wherever they are, they will be there. So the eigenvalues won't change even if I represent the state space definition, even if I represent the same system in a different way in the state space. Any question? If you have any question, just ask. All right. So now let's see the power of state space model by doing state space modeling by doing the modeling of a MIMO system. Here we would have a single input but multiple outputs. Okay. So if you don't have any question with this, all right. So now we are jumping to the next topic. Modeling MIMO systems, rather I would say with ease, using in state space. And as an example, I would choose a mass spring damper system. And now we have seen examples of those earlier. We have solved complicated problems as well. Now we are going to do better than that. We're going to choose something slightly more complicated than what we had. Okay, so I am assuming now here, okay, just a moment. All right. All right, so I'm assuming this is a frictionless surface, and on the frictionless surface you have two mass objects like that. Okay. And again, this is the reference frame, inertial reference frame rather. You would see why modeling this using the transfer function technique would be pretty difficult, really. Right. And you would see why. Okay. And here we have attached a spring here. And let's attach a damper here. Okay. And between these two again, let's attach a spring here. Don't worry, if you have forgotten engineering mechanics, don't worry. I'm going to teach you whatever you need right now. Another damper. Okay. And this surface is frictionless for the sake, for our sake, right? For making it slightly simpler. But if you want, just I want you to tell me, do you want the surface to be frictionless or not? Okay, do you want the surface to be frictionless or not? If you want, tell me. If you don't want, tell me, but be quick. So do you want these blocks to be sliding on the surface with friction or without friction? Okay, someone is saying no, right? You're saying no. So let's put some friction in it, because that way the model will be complete, in my opinion. Right? Okay. Since you said frictionless, let's take a system where there is friction, right? Rather, okay, let's just say that's fine, right? Okay, there is friction right here. In this surface, we have friction here. So we have friction here. That is not how you write friction, draw friction. Okay, but I'm just saying that there is friction. But this friction is of viscous nature. Okay, this friction is of viscous nature, and I'm going to explain what I mean. Okay. All right. So here we have a mass that has a mass of m1. Say this has a mass of m2. This has a spring constant of k1. This has a damping constant of b1. This has a spring constant of k2, damping constant of b2. And here here in this one there is a friction. I am assuming that to be viscous friction. Okay, what is viscous friction? Friction, of course, the opposing force will be proportional to the speed, right? Proportional to the relative speed, right? And that is also true for these dampers, right? The faster you try to move it, the harder it will try to resist you, right? So that's how this damper really works. So here I am also assuming viscous friction, and I am going to assume that the friction here is also represented by a coefficient b4. Okay, a coefficient b4 here, and also the friction here is represented with a coefficient of b3. Okay, so that's how those are the viscous frictions, right? So that is the structure here. Okay, and the way I am trying to figure this out is that I am going to apply a force here on this block. I am going to apply a force. Maybe, so again, the direction is pretty much arbitrary. If you want to consider an opposite direction, just put a minus sign, whatever you get, because that will be a function of time nonetheless. Okay, and here Ft is the force. So this is the force with respect to time. So I applied certain force here on this mass, and whenever I apply a certain force on this mass, what will happen? Everything will start moving, right? Some of the springs will compress, some of them will expand. Okay, they will start moving, right? They will start moving. So both of them will have displacement. But the thing is, m1 and m2 will not have the same displacement. They would have different displacements, because see, the force will be actually transmitted kind of from this to this via this spring and the damper. So it will start moving first in a way. Okay, then it will start moving in a way, right? And that way this will get stretched, then they will pull things back. So the response will hopefully be something like an oscillation or whatever. But the thing is, you would see that modeling this using the transfer function technique would be not impossible, but really difficult, right? So now for our consideration, see, I am going to show you a physical system modeling right now, what I'm showing you. Okay, and here I am going to choose the states. Okay, so what am I going to choose the states to be? So before that, how do I represent the behavior of the output of the system? Obviously I represent the output of the system by calculating the position of the masses here, position of these mass blocks with respect to time. So technically say this is the nominal position. So this is the nominal position when everything is relaxed. Nominal position, I did not apply any external force to it. Okay, and from the nominal position, say when I applied the force, okay, this was the displacement, right? Say this, the displacement is say y1. Okay, of course the displacement is y1 with respect to time. Okay, that's a function of time. or let's just say the displacement is x1. Won't be very difficult to understand. And here the displacement is x2 with respect to time. Once again, all right. So these are the displacements here, and these are going to be my state variables as well. I'm going to assume x1 to be one of the state variables, x2 to be one of the state variables. Got it? Now, of course, in the previous examples, you have seen the phase variable canonical form where we saw that x2 was the derivative of x1. This is not going to be the case here, right? So the state space model that we are going to end up with is not going to be in the phase variable canonical form, because none of the this state will not be the derivative of this state in no way, right? So this is the displacement, instantaneous displacement of mass block m1, and this is the instantaneous displacement of mass block m2. So that's an example, right? This is going to be an example here. Any confusion understanding this? Any question that you might have? Again, the thing that we are going to do right now is to draw the free body diagram, because that is the easiest thing we can do, and from that we can construct the mathematical model. So we are going to draw the free body diagram out of it. Right? All right. So of course, in the free body diagram, we would have the masses and all the forces, right? We would have the masses and all the forces. So let's bring the masses, right? So we have one mass, bring them. So we are constructing the free body diagram. Again, this would be pretty reminiscent to what we did in our previous class, right? When we modeled a single mass spring damper system as an example of a vehicle suspension, right? You recall, right? So that was your M2, and let's just copy this and paste this. That would be your M1, right? So these are the masses here. All right. So there are forces, right? There are forces, and now I have to assume the directions. Okay. So before I can even do anything, let's try to understand. You will see what I mean. Before I can do anything, let's just say the forces. Let's just put the forces. Here we have the external force that I applied. Okay. So that's my Ft. So the external force that I applied. Right. So now let's just also put the displacements here, so that I have some idea about what we are talking about. So x1t is the displacement of this mass, x2t is the instantaneous displacement of this. Okay. So if I talk about this, then I can ask you, what is the instantaneous velocity of this mass? Of course, that would be the derivative of x1t. What is the instantaneous velocity of this mass? That would be the derivative of x2t. Obvious, right? If I know the position exactly, then I also know the velocity and everything, right? Ideally, in an ideal world, then nothing is ideal in reality, right? With that said, I do not really have any issue understanding the direction of the force B3, direction of the force exerted by B3. See, if I assume that x3 is in this direction, so if I assume this mass block to be moving in this direction, so going to the right, if I assume that way, then I can say, of course, this viscous friction is going to oppose this and apply a force in the opposite direction. It is going to apply a force in the opposite direction, right? Now, what is the relative displacement between the ground here, between the reference frame here and the mass? That would be x1, right? So with respect to the ground, this block is moving with a displacement of x1, right? So then if that is the displacement, then what is the velocity of this mass block with respect to the ground? That would be the derivative of x1, and we know that the force exerted by this viscous friction here would be equal to that proportional to the velocity. Now what is the velocity with respect to the ground here? The velocity, because again this friction is happening with respect to the ground, right? With the ground, so the velocity the frictional force here applied will be in the opposite direction and will be proportional to the velocity of these mass blocks with respect to the mass block with respect to the ground, right? And the proportionality constant is essentially B3, right? The friction constant here, right? So the force will be B3 times the velocity of this block with respect to the ground, and the velocity of the block with respect to the ground is x1 dot, okay? X1 dot, the derivative of this, right? X1 dot. So the force will be B3 x1 dot. I am skipping T because that is assumed, I think. Okay, I'm skipping T here. So this is the frictional force. So there, B3 x1 dot. Again, I'm not writing T because I think you can see that. The same thing would happen here, right? Same thing, this mass block has a displacement of x2 with respect to the ground, right? Because whenever I write displacement and everything, we are talking about it with respect to the reference frame, right? Just like if I say voltage, I'm talking about a reference node somewhere, right, which has 0 volt. So here, this is the ground or the reference frame here. So the reference frame is still inertial reference frame at least, and this is the position here, instantaneous position of this mass block. Again, that same way, the mass block has a velocity of x2 dot, and that and the frictional force with the ground would be in the opposite direction. Okay, so this is moving in this direction. So assuming, again, if my assumption is wrong, then we'll just have a minus sign in the result calculation, right? Nothing else. So this is just like your KCL, KVL. If you choose a wrong direction of the current, then in your equation, in your solution, you get a minus sign, nothing else, right? So the force would be in this direction, and that will be B4 x2 dot. The same way, literally. That force is B4 x2 dot, right? That's the force here. Got it? All right. Now let's think about these two forces first. Okay. Let's think about these forces. Now, again, this one part of this spring is attached to the reference frame here. So this part is fixed. No, B3 is not the frictional force. Someone is asking. So this is just the coefficient here. So coefficient of viscous friction here, right? That will be the proportionality constant. Okay. Again, this is the spring constant or whatever, coefficient of spring stiffness. Okay. So this part of the spring is fixed here. So there is no displacement here. So if the mass block moves in this direction, how much is this spring stretched? By a displacement of x2, and then how much force will the spring apply? The spring will apply a retentive force of k2 times x2 in the opposite direction, right? So the spring was stretched because of that. This will apply a force in the opposite direction. So this will apply a force in the opposite direction, and by the spring there, and the force will be k2 times x2, because for a spring the force is equal to the spring constant or the stiffness constant, and spring stiffness times the displacement, right? Same thing will happen with the damper here. For the damper here, notice for the damper here, this is again would behave very similarly to what we have earlier here. So again, the force will be in the opposite direction of the velocity. So if it is moving in this way, say if the velocity is in this direction, then this will apply a force in the opposite direction, and the force will be proportional to the velocity. And here again, one part is attached to the reference frame, so the velocity here will be just x2 dot. So the force would be B2 x2 dot. B2 x2 dot. So those are the forces. But we have problems here. So these two are kind of problematic elements. They are not attached to any reference frame, right? They are attached to two moving objects, right? So here we had no issues because the other parts were attached to the reference frame itself. Now here we don't have anything attached to the reference frames, right? So now we have to assume something, like we assume the positive and negative directions of currents, okay, and positivity of the node voltages, whatever, in our KCL and KVL and KCL respectively. We are going to assume one of them is larger. We have to assume something. We have to assume either x1 is larger than x2 or x2 is larger than x1. We have to assume any one of those, right? Otherwise we won't be able to actually write down the equations, right? So when you write down the mesh equations, we assume a certain direction of current. even if it is not wrong, you are going to assume a certain direction of current, because after you do the calculation, if you assumed wrongly, you just get a negative sign indicating that your original assumption was wrong and the current is actually flowing in the opposite direction. Same thing, if my assumption is wrong that x1 is larger than x2, in that case, if my assumption is wrong, then it will just be the opposite thing, right? Whatever I calculate, we have a negative sign out of it. So we can safely assume that one of them is larger. So we are right now assuming that x1 is larger than x2. You can always do the other thing, no issues, right? X1 is larger than x2. Now if I assume that, now think about this. If x1 is larger than x2, so the displacement that happened with m1 would be larger than the displacement that happened with m2, right? So this m1 block has moved farther to the right compared to how much this m2 block has moved, right? So if this m1 block has moved, like say for example, how should I say, 1 centimeter, then 2 centimeter, maybe this has moved 1 centimeter, something like that. So this has moved farther compared to this, right? So this spring has got stretched. See, that's the idea. So if x1 is larger than the x2, then it means that this block, m1 block, has moved farther compared to m2 block, which indicates that this spring k1 has got stretched, because this part of the spring has moved to the right. So see, this part of the spring will move to the right, this part of the spring will also have moved to the right, but this part of the spring has moved farther to the right compared to this part of the spring, right? This also has moved to the right, but less, okay, slightly lesser than that. So this spring has got stretched, and since this spring has got stretched, now it will try to pull back, and it will pull back from both directions. So whatever force it actually applies in this will also be the force it applies in this direction. Okay, that was also true for this spring as well. So here we said that the spring was applying a force in this direction. Actually the spring was also applying a force in the reference frame also, right? It was also pulling the reference frame in this direction. Okay, but we do not write that because the reference frame cannot be moved, at least for our purpose, right? So now we are assuming that x1 is larger than x2, and with that assumption we can assume that this spring is applying a force in this direction and this direction. The spring is applying a force in this direction and this direction, and this force will be equal. Whatever force it applies will be equal in both ways, right? This force will be equal here, right? So here. So with that said, what is the force here? So what is the displacement? What is the amount of stretch that the spring got? Okay, the amount of stretch that the spring got was essentially x1 minus x2, because this part of the spring moved by x1 amount and this part of the spring moved by x2 amount. So the total amount of stretching that happened to the spring would be equal to x1 minus x2, and the force that the spring is now applying to contract everything back to its normal position would be proportional to x1 minus x2, and the proportionality constant is itself the spring constant here. So the force would be k1 times x1 minus x2. But then again, if you assumed it the other way, if you assume x2 to be larger than x1, okay, then what would happen is that if you assume x2 to be larger than x1, then it will now see, if you assume x2 to be larger than x1, then this part would have moved less and this part would have moved more. That way the spring would have gotten compressed, and because of that the spring will now try to regain its position by pushing, right? So the amount of force will be in the opposite direction. So the spring will now push this back and push this forward, and the force will be k1 times x2 minus x1, because that will be the displacement. Okay, so you see that if you put a minus sign, essentially you get k1 times x2 minus x1, and you just change the directions. So mathematically everything is correct. All right, and the same thing happens for the damper here as well. Okay, so you're essentially calculating the relative velocity here. Whatever velocity I have related to this, that will be x1 dot minus x2 dot. So velocity of this end minus velocity of this end, that would result into the resulting velocity here. Okay, and that resulting velocity would result into the force exerted by the damper here. Okay, so technically the same thing here. We're assuming that x1 dot is larger than x2 dot. Again, an assumption just. Okay, if it is the other way around, we will have a minus sign and the direction will change. So everything is equivalent here. So that would be b1 x1 dot minus x2 dot. That's the relative velocity and times the damping constant there, damping factor there, whatever. And this is the direction of the force. Again, if you assume the other way around, if you assume that the velocity of this mass block is larger than this mass block, then of course the damper will get compressed and it will try to stretch back, and subsequently the forces will be in the opposite direction, and this will be x2 dot minus x1 dot. Same thing. Basic physics, right? So we have completed constructing this free body diagram, right? So this is my free body diagram, but there is just one thing missing. So we have, so what else is missing? The thing that is missing really is the resultant here, right? See that this force is an action, this is an action, this force is an action, so we are applying a certain force here. These are all reactive force here, these are all reactions, so the springs are reacting and they are essentially springs and dampers, they are trying to pull things back because of this action. And out of this we would have something called a resultant force here, okay, and the resultant force will be responsible for moving this mass object in this direction, right? So resultant will be responsible for moving this mass in this direction, right? Okay, so that force is technically equal to, so this is the resultant force. What should I write it? Okay, let's write it here. This is the resultant force, kind of, and that should be mass times acceleration. So this mass has a displacement of x2, so that would be the resulting force here, and this mass will also have resulting force, so that would result into the displacement of the mass, so the acceleration of the mass rather, and that would be of course with the inertial reference frame. So whatever acceleration, so x double dot is the acceleration, x1 double dot is the acceleration there, so mass times acceleration is the resulting force, essentially Newton's second law, right? So that's the free body diagram. All right, so let's do it for the mass 1. So this is like again writing node equations. So for mass 1 I'm writing for m1. So for the mass 1, we can see that for mass 1, what are the first of all, what are the actions? Action is ft, so write it down, minus what are the retracting forces. So one of the retracting forces are this one, right? So whatever force I applied here, we have to subtract this, that is in the opposite direction, x1 minus x2 minus b1 times x1 dot minus x2 dot, okay, minus this friction b3 x1 dot, and that is the resulting force, and that resulting force led to the acceleration here. So and that will be equal to whatever we had, m x1 double dot, right? So to properly mark them, so this is this force, this is this is this one, is this one, this is, and that's the, right? So I think this is understandable, right? All right, I think it's clear, right? So this force was applied, and these were the forces that were pulling, these were the forces that were pulling back, and at the end of the day still the mass moved, so I would have an acceleration in this direction, and because of that, of course, that means there is a resulting force, Newton's second law, so that is a resulting force. That's the equation for the mass 1. Any confusion? There shouldn't be any, right? So with that said, we can now restructure this equation slightly in a slightly better way. So let's bring these terms to one side and keep ft to the other side, because ft is the input really, if you think about it. Okay, that's the force that I applied, right? You applied maybe. Okay, so that way that was the force. So I am bringing everything to one side. So I would have these, and they would all get plus signs. And that would be equal to ft, and I am So x1, x2, all these things are functions of time, right? So keep that in mind, and everything will become yellow. Okay, someone is asking about this. See, I think you have a confusion about how free body, how forces really work. See, what happened? So I applied this force, right? So I tried to pull this mass, right? I applied this force here. I tried to pull this mass, and when I tried to pull this mass, okay, what happened? This spring and this damper and also this friction resisted me. So whatever forces this spring, this damper and this friction resulted into actually got subtracted from the force that I applied, because they resisted the motion. Okay, so this is the force I applied, and these are the forces that actually resisted the motion, but still motion happened. What is motion? Essentially acceleration here. Okay, so this mass still accelerated. So I applied a force, and there were things that were trying to stop me, but they couldn't stop me, because the sum of these forces were not sufficient enough to stop this force, right? So this force was larger than the combined forces here, in a sense. Okay, so I applied this force. Okay, I applied this force here, and they tried to resist me. So these forces were in the opposite direction. Whatever was left over really was the result that made this block move. Okay, so whatever was the resultant force out of these, okay, made this block move, and that can be equal to, that will be simply equal to the mass times acceleration, Newton's second law, right? So this force was applied, they tried to stop me, so whatever was remaining, okay, was the resultant force that made this block move, and when this block moved, the force that was actually resultant can be equal to can be equated simply by writing mass times acceleration. That is why we have this as equal to here. Okay, so this is the action here, these are all the reactive forces that are trying to stop me, and this is the resultant here. Okay, the acceleration is essentially the resultant, okay, because of the leftover here. The same thing happens here as well. All right, so with that equation, let me just let's just try to simplify this equation before I write down the equation for m2, right? So write down this as, now notice very carefully, I might make some mistake. Okay, so please help me out here. So let's take the terms with x1 dot, so that's going to be b1 plus b3 times x1 dot. Okay, x2 dot minus b1 x2 dot plus k1 x1 minus k2 x2, that's equal to f. Let me know if I have made if I have made any mistake, which I can. I'm not infallible. All right, nice, no problem. So let's call this equation number 1. Okay, and I would write the equation for mass 2 here, and then I will bring them back. Now here for mass 2. Okay, so now for mass 2, now I try to think about this. Okay, for mass 2, which one is the action here? For mass 2, which one is the action really? Okay, which one is trying to pull the mass in the, let me see. Oh, right, k1 x2. Okay, right, thank you for seeing this. Okay, someone is saying, isn't, yes, the whatever we were talking about, we are going to do that. Someone is saying, how we can we, so essentially your question is, how can we actually construct the state space model out of this? We're going to see what we can do. See, but you have to understand that there are two dependent variables in this differential equation. This is the second order differential equation, but this is only hiding its true nature here. Okay, it is not a differential equation with, so what is the independent variable here? Time, right? But what is the dependent, how many dependent variables you have here? You actually have two dependent variables, displacement x1 and displacement x2. They are kind of two separate dependent variables. So this is the coupled differential equation really. Okay, This is called a coupled differential equation, we see, and this is coupled with this. Now here, look at the free body diagram again and tell me what are the actions. Of course, the actions are the forces that were transmitted to it by the mass and the by the spring and the damper, right? So because try to see whatever force I applied here, how did that force got transmitted to this? How did that force get transmitted to this? That force got transmitted to this M2 block by virtue of this spring and the damper. I was pulling this, so that also got pulled by virtue of this spring and the damper. So whatever force I applied, so for this mass 2 block here, this force that was actually the retentive force for this, for mass 1, will be actually the action here, right? So what are the actions here? So that will be k1 times this and this. So these are the actions for this mass 2 block, right? So again, for this mass 2 block, let me just write with a different ink. So that will be k1 times x1 minus x2 plus b1 times x1 dot minus x2 dot. That was the force that was trying to pull this in this way, right? Okay. Now what did resist? Of course, these two forces, actually these three forces resisted, right? So these three forces resisted. So I have minus k2 x2 minus b2 x2 dot, and then I have minus b4 x2 dot. Okay, and that still yielded some acceleration in this way, and that acceleration was x2 dot. So if I multiply that with the mass, I get the resulting force. Okay, so that is m2 x2 double dot. I think the explanation is clear, right? Because it is not difficult to understand in the first place. Pretty much, if you are capable of understanding KCL, KVL, then you are definitely capable of understanding this. All right, so what can I do really? There is nothing independent here really. There is no forcing function directly here, right? So ft is not there. So let's bring everything to one side, okay, and take care of the signs properly. That is all we can do. So let's bring this here, and also try to follow this carefully, because I am prone to making beautiful mistakes. So make sure that I don't make mistakes here. So that these will all become plus. Then we'll have plus. And that is okay, fine. Everything becomes yellow at this point. So that is equal to 0. All right. So now let's rearrange the differential equation slightly. I mean, simplify this differential equation. I mean, so I'm saying m2 x2 double dot, then plus b1 x1 dot plus, oh, what have I done? What have I done? Minus signs, minus sign, minus sign, minus sign. Sure. All right. Okay. Mistake. So try to follow along now. Okay, fine. Let me see. Minus b2 x2 dot, I think. Okay, plus b1 x1 dot. Oh, sorry, what am I saying? Minus b1 x1 dot. Minus b1 x1 dot. Okay. Then so what do I have for b2 x2 dot? So I would have plus b1 plus b1 and plus b2 plus b4 x2 dot. Tell me if I am wrong somehow. Then minus k1 x1 and then plus k1 plus k2 x2. Plus k2 x. How many times do I have? 1 2 3 4 5 6 7 8 5 6. So try to follow if it is correct. Let me know if it's correct. Let me do my job here. Let me bring this down below. Cut this, paste this here. Right, so let me know if it's correct. Right, so now look at these differential equations. So this is my differential equation number 2. So this is my differential equation number 2. That's my equation number 2. Now differential equation number 1 and differential equation number 2, they are second order differential equations, but these are coupled differential equations because you cannot solve this differential equation by itself. Similarly, you cannot solve this differential equation by itself. In order to solve one of them, you have to solve the other, right? Because there are dependencies between them, right? So x1 is also dependent here, right? x2, so right? So these are coupled differential equations, right? So now if I ask you to calculate the transfer function, you can see it will be really difficult for you to calculate the transfer function. Why? Because in order to calculate the transfer function, you would need to calculate one differential equation, okay, that directly relates x1 with ft, okay. So you would have to decouple these differential equations, and of course there are ways of decoupling differential equations like this, and those are not very difficult really, but cumbersome in terms of the calculation, mostly rather cumbersome in terms of the calculation. And in fact, let me tell you, one student back in like 2 or 3 years ago, actually I challenged those students to actually calculate the transfer function. One of them actually did, right, decouple these differential equations. You can do some manipulations here and decouple the differential equations, right? The way you actually solve linear equations, you can use those techniques to decouple these differential equations. So you would get two differential equations. But the funny thing is that those two individual differential equations will be each fourth order differential equations. So if you can decouple these differential equations, you would get a fourth order differential equation in terms of x1, another fourth order differential equations in terms of x2. So that in the differential equation in terms of x1 you won't have x2, and in the differential equation in terms of x2 you won't have x1. So you can do the decoupling, but that way you would have two transfer functions. See, one relating to ft and the force with the x1, and other will be force with x2, right? Why? Because it is a single input multiple output system. See, because this is a single input but we have multiple outputs, we are considering this displacement to be one output and this displacement to be one output, right? So it's a single input multiple output system. So how many input do I have? One. How many outputs do I have? Two. So how many transfer functions would I have? I would have two transfer functions representing this entire system. Okay, so one would relate x1 with f and the other one would relate x2 with f. Okay, of course in the frequency domain. So again by doing transfer function you actually lose certain features of this, right? You have to assume zero initial conditions and whatever, right? So instead let's consider a state space. Okay, let's consider a state space, and we know that it's a differential equation. So it's a second order differential equation in terms of x1, Of course, x2 is there in coupled term, and it's also a second order different. The other one is a second order differential equation in terms of x2, but again in coupled form. So combined, they are resulting into a fourth order differential equation in terms of x1 and x2, right? So I need 4 state variables, right? So just to make it very clear, the transfer function modeling would require one to decouple these ODEs, which is very cumbersome, if not impossible. If not impossible to do manually. So, state space. Right? So let's do the state space modeling, right? So now we have to assume the states. Okay. So let us assume the following states. So you already have two states, x1 and x2. And what are those? Those are the displacement of the displacements of the individual blocks, right? The displacement of mass 1 block is x1, displacement of mass 2 block is x2, right? So we already have these, right? x1, so this is the displacement of mass, displacement of m1 block. We have another state which is x2, which is the displacement of m2 block, and we need two more state variables. So we are going to now introduce two more state variables, x3 and x4. Okay, so x3 would be just x1 dot, just like that, and x4 would be equal to x4 would be equal to x2 dot. Okay, so now we are actually trying to automatically decouple it, okay, using the state space technique. Okay, right. Input is considered to be u, so these are the states, rather state variables, right? So what is the input? Input is of course u, so u is the input, and that is will be that is simply be ft, right? So that's the input. And what is the output here? Now output here will be a matrix, not a scalar quantity, right? It's going to be a vector. Output y would now contain two things. Output y would now contain two things. It would contain x1 and x2, because these are the two displacements of the blocks. x1 and x2 are both outputs, right? x1t and x2t are both outputs. So these are outputs, right? So it's no longer a single input, single output system. All right. So let's think about this. Equation number 1. I have to copy this. There is no other way really. Let's bring this equation number 1. Right? I would say this is equation number 1. But what is x1 double dot? Thus this equation number 1 actually, so this is equation number 1, and this becomes, so m1, what is x1 double dot? See, what is x1 dot? X1 dot is already known to be x3. We have assumed state variables, right? So x1 double dot will be simply x3 dot, right? Then plus b1 plus b3. What is x1 dot? So for this x1 dot, I already know x1 dot is just x3. So that's going to be x3 minus, so b1. What is x2 dot? X2 dot is already x4 plus k1 And what is x1? X1 is x1. What is x2? X2 is x2. And what is f? F is u force, right? That's the input. So now this is now a first order differential equation. See, this looks like a first order differential equation because there is only one derivative term there, right? That is the goal again in state space modeling, right? So let's do whatever what we do best here. So write m x3 dot and bring everything to the right hand side here. So I would have minus k1, okay, minus k1 x1, okay, and then I would, sorry, not minus, sorry for that. So I would say I would have k1, sorry, that's a minus, can hardly follow, k1 x1, okay, and then I would have plus that's k2 x2, and then I would have minus b1 plus b3 x3, and then that's plus once more, that's gonna be b1 b1 x4, and that's gonna be plus u, the rest of it. Can you see this? And why did I write it this way? Because I'm going to bring this m down below everything, so that m1 would now go down below everything. I have to divide everything by m1. All right, so this is the equation here. All right, so let's say this is equation number 3. All right, this is equation number 3. See, tell me if you have any confusion with this. And in tomorrow's lab, we are going to see how we can do all these things in Python. Okay. Again, I mean, doing the transfer function modeling here would be very difficult, really too much cumbersome. I mean, there will be like a 99% chance if I do it to make a calculation mistake. All right. And what about the rest of the equation? And I would say, and this was the other equation, equation number 2 for mass block 2. So if you understand, again, if you try to, I would again suggest you to actually take the challenge and calculate the transfer function if possible. If you can, you would see that doing a transfer function modeling would be near impossible here, really difficult. Okay, so in that way, this modeling technique is much easier, really. Even we are not doing any cumbersome calculation. Okay, and this becomes very simple. Again, let's put the state variables here. So I would have m2 and x2 double dot. What is x2 double dot? That's x4 dot. That's just x4 dot. Okay, minus b1. What is x1 dot? X1 dot is known to be x3 plus b1 plus b2 plus b4. What is x2 dot? X2 dot is already known to be x4 minus k1 x1 plus k1 plus k2 x2, and that's equal to 0. All right, so I can again keep this to the left hand side, bring everything to the right, everything else to the right, and divide everything by m2. So I will have x4 dot equal to k1 by m2, k1 by m2 x1. I would strongly suggest that you try to do it yourself and correct me if I'm doing anything wrong, if I'm making any mistake here. k1 plus k2 divided by m2. Because see, whenever I'm doing any research or anything, I never trust myself with calculations. Okay, b1 by m2 x3 minus b1 plus b2 plus b4 divided by m2. Instead of writing it down, please let me know if it is correct, because it would be very hard for me to see that and follow it along. But it will be easier for you to follow along, right? I hope. x4 okay, that's equation number 3. So equation number 4. So we have 4 equations. Equation number 1, 2, 3 and 4. So instead of using all of them, let's write them out the way we want. All right. So we have these equations. Thus, we have these equations representing the system. Thus, we have these state equations all right. So one of them is this equation. This equation is one of the state equation. Okay, nice. This equation is one of the state equations. And of course, obviously, we need 2 more. What are, so we have to calculate x1 dot and we need x2 dot. That would give me 4 equations like that, because it's going to be a 4th order system. But what is x1 dot? Because we have defined it. What is x1 dot? X1 dot is x3, and what is x2 dot? It's x4. So that's by definition we have those equations. X1 dot is x3, right? That's x3, and x2 dot is x4. Why am I writing this way? Because everything is 0 to mean that. Okay, so keep that in mind. All right. So in the matrix form, in the form of a matrix, in the matrix form, we have a 4th order system here, 4th order description. So that's going to be x1, x2, x3, x4. Okay, and that is equal to, okay, so 0, 0, 0, so 0, 0, 1, 0, so 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and then, okay, this is really, really difficult for me to write. Very hard. So I won't do the hard task here. I just copy paste. Sad life, really. Because I can't even copy paste. I will copy paste. That's how you get rid of sad lives. I think you people have better eyesight than I do, so you can see this. So I could really have saved a lot of time if I did make a presentation, like a slideshow. I could have just shown you the slideshow. You would be happy, I would be happy. Okay, I wouldn't have spent so much time writing everything down, but I still like to write everything down so that you get to see the things in progress. Again, I made a gruesome mistake here. All these things should get derivatives because the derivative of the state vector on the left, and that's the state vector. Okay, that's plus. So that's matrix B, and in the matrix B I would have 0 0 1 by m 0 m1 0. That'd be 0 0 1 by m1 0, and of course the input is u. Right, so this thing is the matrix A, this thing is matrix B. Okay, all right, so that's the system, that's the state equation, that's the state equation. So this is the system matrix, this is the input matrix, so this is the state equation, right? So, and if you still calculate the eigenvalue of this matrix A, so this is matrix A, and if you calculate the eigenvalue of matrix A, you would still get the poles of the transfer function. Okay, so there is one thing you can note from here is that even if you have two transfer functions for the same system, because it's a MIMO system, the poles will all be the same because we only have fixed number of poles here, right? Those are the eigenvalues of this, right? And we are yet to write down the output equation. But what is the output equation? The output is this, right? The output is this. So x1 and x2 are the output. So these are this. So the output equation is really writing. So I'm going to say, and output equation would be y, which is now a matrix, which is x1 and x2. These are the outputs, right? So x1 and x2, right? But how can you get this? Simply from the states. How can you get these? Because the state vector is this, right? This will be we have to represent this in the form of Cx plus D. Of course, we don't have D here again. So all we have to do is to multiply this with a suitable matrix that actually does that job. So we have, so what should be the dimension here? And I just messed up. What should be the dimension here? So again, try to see that this dimension is 1 cross 2, so 2 cross 1, 2 rows 1 column. Here this is 4 times 1, so 4 rows 1 columns, and then obviously this has to be 2 times 4, right? So this has to be having two elements like that. So of course this has to be 1 0 0 0, and this will be 0 1 0 0. So if you do the multiplication here, this becomes x1 in the first row. So if you multiply the first row with the first column, the column here, this becomes x1, so that's x1, and this with the column once again, so that becomes x2. So that's it, right? So so 0. So get rid of these, get rid of these, get rid of these as well, like we never thought about this. And of course matrix D is 0, and that's your output equation. Matrix D is 0, so you can just say plus 0u if you wish. Okay, so matrix D is 0. Okay, maybe you don't want to write that. So that's the output equation. Right. So that's the complete state space model of this system. And if you do that calculation now, if you do the CI, now if you calculate the transfer function, there is the one funny thing here. If you do the transfer function here, you would like this, C Si minus A whole inverse times B plus D. Okay, you would no longer get a transfer function, but you would get a transfer function matrix itself. Okay, and you would get two transfer functions. This is going to be of the order 2 by 1. Okay, you'll see. You can try this at home. Okay, so that completes today's module, and I'm going to talk about how these can be implemented very easily in Python in tomorrow's class. So that's the end of today's discussion. You can see this state space modeling was actually doable with not much of any complication. But if you wanted to construct the transfer function out of these, the decoupling part would be really cumbersome, really difficult, I would say. All right. So that's the modeling part. Again, if you have any query, ask. We're going to see other types of systems, mainly electrical systems and electromechanical systems later on. All right. So that's the end of today's discussion. Just feel free to ask any question that you might have. I see already most of you have left. I mean, by the 1 hour mark, most of you had already left. It doesn't matter really. Again, the thing is that try to grasp the idea that state space modeling is really the way control system works nowadays. Like, if you want to analyze any control structure, whatever, or physical system, state space modeling would be the way to go. Because for complicated systems, handling it with transfer functions would be very difficult. But still, transfer function has its usages in certain cases. All right, so that will be the end of today's discussion. Feel free to ask any question that you might have via an email, and of course you are going to get an assignment on state space as well. Okay, so you are yet to get an assignment on what should I say, all the topics that we did after root locus, right? We are going to do that. Okay, so thank you very much. I think your questions were cleared up properly. All right, and we're going to take 2 more classes on these fundamental state space things. Okay, all right. Then we are going to go back to classical control again. We are going to study something called Bode plot and Nyquist plot, and then once again we are going to come back to state space if time permits. Okay, so that's the end of today's discussion. Thank you very much. I will see you tomorrow.